Good morning, everybody. We'll have a really quick intro here. This is Codeforces round, CodeTON, CodeTON round 2. It's a Div 1 round rated for me, and it's got prizes, so we're going to try and win one. Aquamoon has two binary sequences, A and B, each of only zeros and ones. Aquamoon can perform the following operation any number of times. A1 is the first element of A1, okay. If A contains at least two elements, change A2 to the min of A1, A2. And remove the first element of A. If A contains at least two elements, change A2 to the max of A1 and A2 and remove the first element of A. So if the first two elements are the same, you drop the first one. Otherwise, you drop either the first or the second. Can Aquamoon make A equal to B using only these operations? So we need two ones. Yes, you can keep. So it's a suffix, and then you can keep one thing in the prefix. So 0, and then keep this. Yes. Okay. And then yeah. All right. Okay. So we have. Int n equals this. Int n2 equals this, for array A, B. All right, and then yeah, for int I equals 0, as less than n2 I plus plus. Yeah, we'll make this the outer loop, and then we'll say if A at n2 or A at n minus 1 minus I is not equal to B at n2 minus 1 minus I, then out.print line no, and then continue outer. Otherwise, for int I equals 0, so we need, yeah, for int I equals n2, I is less than n, x plus. That print line no, and then if A at 0 equals if n1 is n2 less than n1, less than or equal. If n equals n2, then continue outer. And then the last case is they're not, so yeah, so we need this. A0 is equal to, or B0 is equal to A so I plus 1 is less than this. Then we don't need this case. Yeah, and this is n2 minus 1. Okay, so then less than n, so if B at 0 equals A at n minus 1 minus I, then I've got print line yes, continue outer. Yes, yes, no, no, no. Yes, yes, no, no, yes. Okay, looks good. Submit A in Java. And we're in. Okay, problem B. Wait, did that really take 4 minutes? I guess so. All right, problem B. Luke is a foodie. Luke likes to eat. There are n piles of food aligned in a straight line in front of him. The ith pile contains AI units of food. Luke will walk from the first pile to the nth pile. He wants to eat every pile of food without walking back. When Luke reaches the ith pile, he can eat that pile if and only if something. The absolute value of v minus ai is less than or equal to x. So x is a fixed integer, and v is Luke's food affinity. Okay. Before he starts to walk, he can set v to any integer. Also, for each pile I, he can change his infinity to any integer before he eats the pile. Oh, so yeah, so you want to see if it's how close it is to this, otherwise you have to change it. Well, that's annoying. Dang it. Okay. Be right back. All right, we're back. Okay. Dang it. Well, we're gonna go with no camera for a minute, and oops. See how this works. Maybe in a bit we'll get the camera back. All right. Yes. So we need to see how many we can take. So the range will be 3 times 2. 3 plus 3 plus another 3, yeah, so 6. Okay. Yeah, so we can just do one of these. Alright, so then min equals math.min of min or I, and then math equals, or max equals math.max of max or I. And then if max minus min is greater than k plus k, then max equals min equals I and count plus plus. And then out print line count. All right, we are running, and we'll read C. We'll do that. Looks like we got it. All right. There are n houses numbered 1 to n in a circle for each I. House I and house I plus 1 are neighbors. Additionally, house n and house 1 are neighbors. Initially, m of these n houses are affected by a deadly virus. Each morning, Cerno can choose a house which is uninfected and protect the house from being infected permanently. Okay, so you can protect a house every morning. Okay. Each day, the following things happen in order. He chooses the unaffected house and protects it. All unprotected houses which have at least one infected neighbor become infected. He wants to stop the virus from spreading. Find the minimum number of houses that will be infected in the end if she chooses optimally the houses to protect. Okay. Yeah, so we do a BFS, and then we store how many neighbors there are at each step. Yeah, okay. So this is easy. We'll say int n equals this, Ooh. Yeah, okay, that's fine. K equals this. And then int array a fs dot read array n. So hash set integer lost equals new hash set. Do we have to binary search this? Yeah, we probably have to binary search int min equals 0, max equals n. Min plus max over 2, if possible. So what do we need? Int array a, int n, and then int turns, probably. So a n turns, okay. Is a sorted? Is it sorted? No, it's not. Okay. So if it's possible, do one thing. Otherwise, you do something else. We have to ruffle sort. Okay, and then this will be mid. So if it's possible in mid turns, then max equals mid. Otherwise, min equals mid plus 1. Okay, so this is all right. Good, and then we need to write that print line, mid. Or out print line, mid. Well, I guess that's not true. Yeah, we need int n infected. Then we'll say, do this again with min, and then print out an infected. All right, cool, this should be good. All right, so now we have to solve this part. So we know it's sorted, so we can say yeah, what do? We need to do a sweep. All right, so int last hit will be -1, and then we'll have n infected equals 0, and then int n borders equals 0. Okay, and then at the end we need to say return n borders is less than or equal to turns. We have one border, one turn. Oh, turns is how many turns have passed. So if this is less than or equal to turns plus 1, then it's possible. And then last hit, yeah, so we need to update this. Okay, so int L will be a at I minus turns. R will be a at I plus turns. And then L equals math.min. Oh, these are all one index, aren't they? Sure, we'll do one index then. So math.min, or L equals math.max of last hit plus 1, or what's R? Or L. Then R equals math.min of R, or N, whichever is smaller. Okay, Yeah. And then if L is greater than last hit plus 1, then N borders plus plus, because you have a new left border. And if R is less than N and I is equal to, the houses are arranged in a circle? On a circle. Dang it. Okay, so we can ignore this part. So this is so this will be A at A at length minus 1. So the last thing, minus N plus turns. So this is the last thing hit. Sure. Okay, we don't need to bound the R now. And then, yeah, so if this is bigger, then we have a new border. Oh, do we have one new border or two? That's not true. Yeah, this is annoying. Okay, so is it possible that you want to so if this is what it looks like, you can stop it here and here with just 2 and leave this for 1. Yeah, so I guess this approach is wrong. You would want to do these as fast as possible every turn. So you'd want to like block it here when you can, and then if stuff spreads, that's fine, and then you block it here. So you want all of the gaps, yeah, so you want the gap sizes. And then yeah, I guess gap sizes from biggest to smallest. And then you want every turn, if the gap size equals 1, then you just like take it, or just like save that. I guess this is the biggest, right? And then what if it's not 1? Then otherwise you get like save 1 the first turn, or yeah, otherwise you like save n minus 1 or size minus 1 over 2 turns. Or it's equal to 2. Okay, and then all other gap sizes, decrease by 2. Yeah, okay. This is just not correct. Not helpful at all. Yeah, this is just not right. And then we just need the gap sizes. Okay, so int array gaps equals new int array size k. And for int I equals 0, I is less than k I plus plus, gaps at I equals a at I plus 1. Ooh. So if I equals 0, we do one thing, otherwise gaps at I equals a at I minus a at I minus 1. This one is gaps at I equals a at 0 minus a at n minus 1, k minus 1, plus, or minus n. Alright, so we've got our gaps, and then we'll ruffle sort them. And then for int I equals n minus, or k minus 1, greater than or equal to 0, I minus minus. Int n save equals 0. Yeah, so then out.print line n minus n save. And then int n sub will also be 0. Okay. So if a at I is less than or equal to n sub, then continue. We'll just say a at I minus equals n sub. If a at I is less than or equal to 0, then continue. If a at I is equal to 1, then n sub plus plus, n save plus plus, and continue. What if it's equal to 2 or more? I guess we can say or it's equal to 2. Then we just say 1, okay? And then otherwise we can save n minus 1. So otherwise n save plus equals a at I minus 1, n sub plus equals 2. This is an a at I, it's gaps. So the first one you can get 7. I say you can stop 5, but you can stop 7. Or I say 5 need to be infected, but really 7 do. Oh, yeah. Six. Okay. Let's look at this case. Six. So how does this happen? Five, 3, 2. 3. So we have 1, 2. Oh, are these all -1? Yeah, -1 and then -1. Okay, I think that's right. 2, 15, 5 looks reasonable. Submit C. Then I'm gonna see if we can get this camera back. Back for a bit anyway. Got C. Let's move on to D. How are things looking? Not good. Okay, we were very far behind. Very far behind. All right, let's get D though. Eric is an array B of length M, then generates n additional arrays, each of length M, from the array B in the following way. Initially, Ci equals B. What is Ci? Oh, okay. So initially, they are just copies of B. Eric secretly chooses an integer k and chooses ck to be this from, wait, what? Chooses an integer k and chooses ck to be the special array. Okay. There are 2 operations he can perform on array ct. Okay. He can choose 2 integers, I and j, subtract 1 from both, okay, and add 1. So he can like pick an array on some array CT. He can move, yeah, and move one thing both from back of them. Okay. All right. Choose 2 integers and subtract 1 from both of these. And add 1 to both of C. Oh, this is weird. So you move 1 forward, and you move the next forward 2. Yeah, so you pick one thing to move forward 1, you move another one to move backwards 2. Okay, you move 1 backwards 1, you move the next one forward 2. Right. Oh, this one you move 1 backward 1, 1 forward 1. I see. Alright, you're given a bunch of arrays you need to find. He uses this at least once. Okay, so we can find the special array. Okay, we need to find the special array. That's easy. Okay, the value of k. Easy. Also, you need to find the number of times operation 2 was used on it. That's also pretty easy. Yes, okay, this is easy. We can do this. Easy, 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 easy. So we need to know the key part is operation 2. Operation 2 moves the center of mass right by 1. Yeah, so in particular, we want the sum of indices times count at index. Yeah, and this doesn't change for operation 1. For operation 2, it moves over by 1. Okay. And then we print 2 numbers. Okay. Int n equals this, size equals this, int array a's equals fs dot read array Nope, A is equals 2D array equals new int array n by something. I equals 0. Less than n plus plus. We'll say A is at I equals fs.readArray of size. Okay, and then int long array values is new long array n. We'll say values at I plus equals j times is at ij. This needs to be a long. Are all these things the most 10 to the 6th? 5, 10 to the 5, 10 to the 6th, I think. Okay. All right, so this is all good. Yeah, all right. And then what? Here are the values. We have the so now I need the thing with the base value. So int ants will be 0. If values at I is greater than values at ants, then ants equals I. And then not ants will be 0. Okay. Out.print line, this will be ants. Plus 1 plus a space plus not ants plus values at ants minus values and not ants. Three, 1, 3, 10, 15, 20, 25, 30, and a big number. Okay. Submit D. Much easier than C, I'd say, but that's fine. Okay. Yeah, we'll let that judge. We'll look at our lights for it. Count seconds. Cerno has a directed acyclic graph, the n nodes and m edges. The graph has exactly one node that has no out edges. Has exactly one node that has no out edges. Okay, so it's kind of like a tree. It's like a tree with extra edges. The ith node, how are we doing? Still behind, but that's fine. That's fine, okay. The ith node has an integer AI written on it. Every second the following happens. Let S be the set of nodes that have AI greater than 0. For all x in S, 1 is subtracted from AX. And then for each node Y, there is such that there is an edge from X to Y, 1 is added to Y. For all, what is AX? So everything has an integer on it. Then for everything that's positive, subtract 1 from it, okay? Then for every node Y, such that there is an edge from X to Y, 1 is added to this. So anything that's positive, you subtract 1 from it, you add 1 to everything adjacent, okay? Find the first moment in time when all AI equals 0. Oh, wow. Is this just a BFS though? It's acyclic, it's directed. Yeah, it's just a BFS. Why is it hard? Can we have a picture? It should just be a BFS, I don't get it. Why is this only if 13 solves? People getting it wrong? No. Is everyone just dumb? Seems unlikely. There's no way Eknerwala doesn't get this in 5 minutes. It's worth enough points. What's going on? I must be wrong here. It's got exactly one node with no out degree edges. So some things go into that, right? Those things have an out degree of 1. And it's got no cycles. All right, let's look at this. So we've got 1, 2, 2 to 3. Oh, and that's it. Okay, so 1 to 2, 2 to 3. So in the first turn we have 1, 1, 1. The next turn we have. You guys probably would like to see, huh? Actually, we've got 1, 1, 1. Then we've got so minus, 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 and then plus, plus. So then we've got 0, 1, 1, then 0, 0, 1, and 0, 0, 0. Can something hit 0 and then become 1 later? Yes, it can. Can it be quite large? Sorry about the flickering here. These have big numbers. Can it really become large? Why can it become large? Okay, so this is what, a click of size 6. So 1, 2, 3, 2 to 3, 4 to 3, 6 to 3, 3 to 5, 6 to 5, 6 to 1, 6 to 2. You start with 10. So initially you've got like a bunch of 10s. And then, ooh, yeah, I guess it's tricky because things can be 0. They can hit 0 and then come back. And then how big can these numbers be? The edges can be up to, 1 billion. I see. Tricky. Not sure. Yeah, it would be nice to not have to subtract. Like, time is a little annoying. If only we could just do, like, rather than time, do, like, total value. Because we can figure out the total value at the end pretty easily. The problem is this. The value doesn't decrease by 1 if you're 0. So we can get the total value, but we need, like, in so many turns, how many times will you be 0? Can we do that with a hash map? Yeah, what is the range in which your turns are not 0? Maybe. So everyone can have, every node has time and amount given. At most once for every other node, right? No, I guess it's not at most once. Well, it's the start points are at most the distance. Yeah. So if you coordinate compress, it'll be small. All right, so then in top sort order, we find ranges, ranges like m most n, and then distribute ranges to all neighbors. Okay, so we can solve this. The real question, is it beneficial to do so? Yeah, because everything else is hard. Okay, good. Let's do it. So the question is, how do we code it? Shouldn't be too bad, right? Static class node, have an array list node adjacency equals new array list. If you ding me on time because this is multi-test case, I will be very upset. Okay, here's the mod. Where's my mod? Mod is this thing. Okay. And then we'll take n and m. Okay. N equals this, m equals this. And then what? Node array nodes, new node array n equals 0 less than n plus plus. Say nodes at I equals new node. And then for int I equals 0 less than m I plus plus, we'll say nodes at, or okay, yeah, int a equals this, b equals this, nodes at A dot adjacent dot add nodes at B. It's unidirectional. Okay, and then we'll have an array. Did they say exactly one? Exactly one node. Okay. Well, it doesn't matter. Array deck node BFS new array deck, and then we'll say for node nn in nodes, if nn dot adjacent dot size equals 0. We also need, okay, so we need int out degree alive equals 0. Wait, what order? Do we want the one with no in degree even? Yeah, I want to press the ones with no in degree first. Okay, int in degree equals 0. Yeah, okay, and then nodes at B dot in degree plus plus. Okay, and then what? So we have this BFS. Oh yeah, so we need to build this. So if nn dot in degree equals 0, then BFS dot add nn. Okay. Good. Then we need to do this BFS. So while not BFS dot is empty, node now will be BFS dot remove top sorted dot add now. We'll say for node nn in now dot adjacent nn dot in degree minus minus. If nn dot in degree equals 0, then BFS dot add last nn. This will remove the first one, and then this will go through our BFS. Then we'll have the top sort. Okay, cool. And then we just need to do stuff in top sorted order. Okay. For node nn in, I guess nn in nodes. We also need the amount. Okay, so int start amount is 0. Public node int start amount. This dot start amount equals start amount, and then array list of, okay, so this will be static class gift int amount int start time, and then public gift int amount int start time. This will be a long actually, and then this dot amount equals amount. This dot start time equals start time. Okay, and then we need Boolean intersect with gift O. Ooh, how do we do this? Ooh, this is annoying. This is really annoying. Really annoying. Wow. Wow. Okay. Have to be really careful about how things overlapping the mod intersect. Yeah, this is really easy to get wrong. Okay. Anyway, this is a array list of gifts. Gifts. Array list. We'll say gifts.add new gift. This will be from, ooh, how do times start? What's first moment? So it starts at time 0, and then the amount is start amount. Or it starts at time 1. Does it start at time 1? 2, 1, 0. So yeah, plus 3 is time 3. That's fine. Okay. Yeah, sure. All right. New node. What is this? This is new node with fx.next in. That much stuff. Okay. All right. So then we have this top sorted. This in top sorted. Each node gives each other node and things. Not each other node, each of its edges. Okay, yeah. For, okay, so we need void try give to node O. Assume O is an out edge. Give all gifts. Okay. Yeah, so for node 2 in nn dot adjacent, nn dot try give to 2. Okay. Yeah, and then we're done, right? And then, oh, so what if this is 0? 0, 0, that's probably fine. Okay. I guess we'll say, yeah, if start amount is equal to 0. Okay, and then we'll have long ants equals 0. For node, and then in, I guess, the last node, right? Oh wait, do we add one? Who do we add one to? There's one graph that has no out edges. Yeah, but then you add one and edge from X to Y, yeah. So there's just one guy. So this is, yes, the ants will be if top sorted dot get top sorted dot size minus 1 dot gifts dot is empty, or dot is empty if it's not empty, I guess. Then gift G will be this. Well, okay, array list gift gifts equals this. And then we want the gift with the max ants. So then for gift G in gifts. Oh my goodness, this is hard. Dang, this is really hard. We have to compare these numbers. Dang. This is really hard. We need the biggest one. Oh, this is hard. Wow. Wow, this mod is insanely annoying. That's so difficult. How do you compare things not under mod? This is a really annoying problem. Because, like, look, so even just with the like, I haven't even handled giving the gifts, but you have to find the gift that ends at the last time, right? But all the times are stored under mod, so you don't actually know when they end. Wow. Wow. You can have two paths that are, like, super similar. Okay, how big can it really get? How big can it really get? Like, can it get that big? Can it get that big? Maybe it can't. If you have a thing with an out degree of 2, so if this has 10, it gives 10 to each of these. And then each of these give 10 to the next guy. So this has 20. So just by doing that, you can double things. So they can get massive. Wow, this is so annoying. You might need to compare like massive numbers, like gigantically different numbers. I don't know, this problem looks super approachable, but just isn't. Like, this is so annoying. My goodness, it's tight too. Such a tight time limit. We need like some sort of segment tree. Maybe you process everything at once so that you can tell. Alright, let's try a different approach. Yeah, the hard part's going to be evaluating this over time. So maybe this approach just doesn't work straight up at all. I'm glad we saw it now. So yeah, we need to, so we've got some DAG. We need to process stuff until one gift ends. Yeah, what if stuff's just happening in different places and it's, do we need like, well, we'll be dealing with these massively big numbers. We need to compare them and also have their values in our mod. Is there any way of doing that other than with the segment tree? Yeah, so we've got like, ooh, this is hard. Okay, so, yikes. There are just so many ways of getting it wrong too. Like even if you pass data, it's like a 20% chance that you are actually right. Like samples don't tell you anything. Unless maybe, I don't know, maybe if you do it in a clean way, but. So this is not helpful anymore. So what do we need to do? So we have a bunch of like gift, which has a start and then I guess an end. Or start and a size. So we need to add two gifts together. So the start equals, yeah, start equals the min of a.start, b.start, and then size equals a.size plus b.size. So this gets gigantic. So we'll need to add two numbers. The starts will always be small. So that's fine. Oh, hang on a minute. Everything goes to the same person. Yeah, that makes sense. Okay. So we don't need to compare really. Maybe this does work. Okay, so yeah. Everything goes to the same person. This is very important. So this means we only need to be right. Yeah, what does this mean? We only need to be right. So we only need to compare things if they're small. If they're less than n. Yeah, if they're bigger than n, this means that they'll overlap. Okay, all right, so it's not that bad. All right. Okay, I think we should be fine. We need to compare, we need to join them. Okay, so we need like a void compress gifts. Okay, so we'll say, yeah, so node last will be this. so then we'll say last.compress gifts, and then ants equals last.gifts get last.gifts dot size minus 1 dot start time plus last.gifts dot get last.gifts dot size. Okay, so gift last g equals last.gifts dot get last.gifts dot size minus 1. And then it's the last gift, so then we'll say ants equals last g dot start time plus last g dot amount under mod. Okay. All right, so this part's actually fine. We just need to try give things to people. I think so. I think that's it. I think that's it. So how do we, oh, we also need to compress. Ugh. Yuck. Okay, so maybe this is, well, let's do compress first. So this has to be, yeah, so make this amount equals like less than mod is real value, or mod to 2 times mod minus 1 equals compressed. Because it shouldn't matter. Yeah, okay. Sure. So then we'll say collections.sort gifts by start time. Is this gonna, are they really gonna get us to TLE here? How many gifts do you have? The number of edges you have. How many edges do you have? You could have a lot. Dang, okay. Sort by start time. If I TLE, I'm gonna be very upset. Okay, so we have them ordered. Yeah. So what does intersect do? Long my end equals start time plus amount. His end equals o dot start time plus o dot amount. And then if my end, yeah, return not my end is less than o dot start time, or his end is less than start time. So if either of these are the case, they're disjoint, otherwise they intersect. Yeah. Okay. Compress gifts. So we sort these. And we'll have an array list gift real equals new array list gift. This will be gifts.size. It's the expected thing. And then we'll say gift last equals gifts at 0. If gifts dot is empty, then return. Okay, this is the real one, or the real ones. Okay, then we'll have gift last equals gifts get 0. Real dot add the last one at the end, and then for int I equals 1, I is less than gifts dot size I plus plus. Gift next equals ifs got get I, if last dot intersects next, then last dot size. Okay, let's say void add size want to add, and then so this will say if amount is less than, okay, yeah, so amount plus equals to add. If amount is greater than mod, then amount equals amount mod plus mod. Cool. All right, so what happens here? If the last one intersects next, then last dot add size next dot amount. Okay. Otherwise, real dot add last and last equals next. Okay, so we can compress these. All right, so then for node nn for gift g in gifts, then we want to do o dot gifts dot add g. Does this just work? There's no way. Okay, it doesn't. Yeah, so let's see what's going on. So this is the kind of most basic case. We print 1. The answer is clearly not 1. Oh, well. Yeah, so when you give it to someone, where's the give? Where is this? This is the try give to, yeah. Okay, so we can't give everyone the same one, right? Because they modify it. Yes, this has to be a new one. So add, no regifting allowed. New gift. This will be g dot amount, and this will be g dot start time plus 1. Okay. 3. Yeah. Three. 5. Ooh, no. All right, so this is it this one? 359. Oh, because of the mod. Dang. These are very helpful samples. Okay, so some stuff is happening. Yeah, I think we're just wrong somewhere. Let's see what this looks like. There are easier ones we get wrong. This is 4. Well. There you go. In the third test case, the moment when these become 0 is 2 times this plus 4. All right. If you say so. Let's take a look. So we have 1 to 2. Ooh, can we just get a graph here? That would be cool, wouldn't it? It's directed. So these things are, so it's 1. Oh wait, where do they start? Okay, so they start at node 1, 2, 3, 4, and 5. 1, 2, 3. So the first one is 1, 2, 3, 4. Yeah, okay. One, 2, 3, 4. And then it doubles here and it doubles here. Yeah, okay. Oh, we don't compress ever. Does this fix it? The answer is just not 9 though, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7. I can't count. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, I'm picking the biggest instead of the smallest. What things am I getting wrong here? Okay, 14 is just straight up not right. Okay, they never destroy the gifts, so we should just be able to print them all afterwards. Return start plus start plus end is plus end time. Or plus amount. Plus amount. Okay. So this starts at 3, 4, 4. Let's do these side by side. I'm covering it. Well, yeah, I guess we'll do this then. All right. Um, 3, 4, 4, 5, 3. That's right so far. 3, 4, 4, 5, 3. So we're here. That's all fine. And then 4, 5, 6, 6, 7. So 3, 4, 5, 6, 7. Ah, the amount's 0. Okay, that's the problem. So amount's getting set to 0 somewhere. It shouldn't be. Amount. Yeah, what is amount equal to? Try give to. It is amount start time. Okay. So why is this one's amount 0? Did I compress wrong? Greater than or equal to mod? What if it's equal to mod? Amount should not be 0. Ooh, yeah, this is the problem. Well, is it? No, the amount just shouldn't be what it is, so that's fine. Oh, wait, this is wrong. This is, yeah, okay. This should be start time 0. Start amount at time 0. This is not compressed. What? They totally overlap. Oh, yeah, okay. Then gifts equal real. Duh. Okay. Ba-da-ba-da. Full screen. Give me E. Two. 10, 110, okay. All right, is the sort gonna kill us? Because we decided to use Java. Dang it, for real? Okay, alright. Ooh, speedy! Nice, okay. Really, we're that bad? I thought I was doing alright. Dang, why? Oh, I guess just everyone's getting it now. Okay, fine. Alright, alright. Coloring game. Alright, this is actually pretty fun though. Alice and Bob are playing a game. There are n cells in a row. Initially, each cell is red or blue. Alice goes first. On each turn, Alice chooses 2 neighboring cells, which contain at least 1 red, and paint the 2 cells white. Bob chooses 2 neighboring cells, which contain at least 1 blue, paints those 2 white. The player who cannot make a move loses. N cells in a row. Okay. Can one of those cells be white? Note that a chosen cell can be white as long as the other cell satisfies the constraints. Okay. So the most turns a player can make is the number of cells of his color. And so if you have like 10 red and 3 blue, Alice can make up to 5, Bob can make up to 2. Alice would never delete 2 reds in a row. Bob would never delete 2 blues in a row. So Alice says reds minus minus. And Bob says blues minus minus. Okay. And Alice might say maybe blue minus minus. And Bob might say maybe red minus minus. Both will do this if there's an adjacent red and blue, right? Yeah. So this seems trivial. Blue, red, blue. Blue, red, blue. Oh, it can be shared. Tricky. Okay. So if you have a group of... so that's tricky. Okay. So, yeah. All right, so we're making progress here, though. Seems like maybe we can get this. Here's the idea. If we have a group of... Look, so if you've got... Like, if everything you have is... If everything you have is... Like... red, 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 blue, blue, red, 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 blue, blue, blue. Like this, for instance. Then you've got, this part's interesting. So you've got 1, 2, 3 switches. Yeah, so you have 3 switches. So you have 6 red, you have 5 blue, and the first 3 turns are both. And then Bob starts. So you do 6 minus 3, 5 minus 3, and then Bob starts and Bob loses. Because you need to have more. Yeah, so if you start, you need more. If you start, you need more. The tricky part is when you wind up with something like this. So what if you have like red, blue, red? Then in this case, you've got this, but this overlaps. So you can pick like one of these kind of. It feels like it resolves to some sort of nim. So yeah, but then like you can get, it can be even more complicated. Like you can have a red, blue, red, blue, red, blue, I guess is the next one, right? So this can be 2 or it can be 1, right? So this can be, this can be 1 or 2. Then we end this with like another blue and then another red here. This is 1 or 2, right? So you can make it, you take the middle, that's 1 move, or you can do this and there are 2. So if you have 2 more reds than blues, I think red wins. Yeah, and then if you have more blues than reds, blue wins. What if you have the same number of blues and reds? Or one more red than blue. So yeah, so blue greater than R. This means blue wins. It's Bob. R plus 2. Or R plus 1. Wait. Blue's less than R minus 1 is Alice. If you're more than the number of reds, yeah, maybe we should just write this in the terminal here. This is problem F. Okay, so if more, yeah, so blues is greater than, we have more blues than reds. We're going to remove a bunch of one of each, and then we're going to move a bunch of, yeah, okay, so remove some BRs, and then remove, and then take turns. So if you have more blues than reds, then this means that Bob wins, no matter what. Right? Yeah, Bob wins. If the number of blues is less than reds minus 1, then Alice wins. What if it's equal to red minus 1? Yeah, then Alice wins. So if they're, yeah, so let's check this in samples. So we have Bob wins, Bob wins. So this is tied. So we don't know. Okay, 3, 1, 2, 3, 4, 1, 2, 3, 4. Tied again. Tied again. 1, 2, 1, 2. Oh my goodness. Yeah, probably both dead. Yeah, so this is easy. So if they're not equal, then we have a winner. Okay. Equal is the hard part. All right, so cool. What if it's equal? Then it winds up being nim somehow, huh? So we know the number of reds and blues are the same. So yeah, so all that matters is number of, I guess really all that matters is the parity of the number of turns, of like taking 2 adjacent ones. Okay, so we have a bunch of, oh, we've got a bunch of games. We have a bunch of games. We have a bunch of games. Look at this. It's nim. It's nim. You want to see the games? Let me show you the games. We have a bunch of games, right? These are we'll have 2 blues in a row and it's the same. Okay. So you have this. You can take a group. So what is the grunting number of, well, everything's got to have at least 2, right? So you've got this. This will have a grunting number of 1. Yep. If you have blank, this will be a grunting number of 0. If you have 1, this will be a grunting number of 0, because you need 2 adjacent ones. Okay. This is 1. What if you have 3? You can reach 0 or 0. So this is also a grunting number of 1. What if you have 4? These have to be alternating, right? Alice, Bob, Alice, Bob. Alice, Bob, Alice. Yeah. Oh wait, so what do you want to do here? What's the goal? The parity. So if you go first, you want it to be odd. So you want to make the last move. So it's just like normal. Okay, yeah. So 4, you can reach 1, or you can reach this. What is this? 0x or 0. So you reach 0 or 1, so this is 2. Okay, so just value divided by 2, or count divided by 2. 1, 2, 3, 4, 5. So what is this? You can reach 3, that's 1. You can reach 2 and 1. What is the 2 and 1? 2. Should we just, let's just quick brute forcer here. Quick brute forcer for this because we might as well, right? What problem is this? This is F. So F brute. Yeah, we don't need any of this. Iterate A, continue into array 100, and then A at 0 equals 0, A at 1 equals 0, 4 into I equals 2, is less than A dot length, I plus plus, 4 into I equals 0 is less than A dot length, I plus plus, out, this out, I plus a space, plus AI. Okay, so then what is this? Hash set integer can reach, equals new hash set, and then we'll say, oh, I guess, well, if we have the groaning numbers, then we're set, right? Yeah, so this can just be the real solution. And then int max equals 0, well, can reach dot contains max, then max plus plus, and then AI equals max. Okay, so then 4 int split equals 0, split is less than, or split plus 1 is less than A dot length, split plus plus, and then this will be, what is this? Oh, we gotta find a faster way of doing this, right? Because this needs to be, there's gonna be lots of stuff here. It'd be 5 times 10 to the 5th. Yeah, so we need a faster way of doing this. We'll see if there's a pattern quick, I guess. Could have a brute forcer either way. So split, yeah, so then int left equals split. Int right will be I minus 2 minus left. Because I minus 2 will how many will be left, the rest will be on the right, okay. And then int per, okay, so yeah, int left ants will be A at left, right ants will be A at right. This isn't right, is it? Yeah, it is, okay. So then can reach dot add left ants XOR right ants. Oh, yeah, you can reach that. And then it's the amended from what you can't reach, okay. All right. -1. Dang, this is complicated. Okay. Is this right? Should be. So 5 we're saying is 0. 5 can't reach 0. Is that true? 2 and 1. So yeah, you can reach 1. You can reach 2 and 1. Okay, you can reach. Yeah, I mean maybe it is. So 2 and 1 or 2 and 1. Yeah, so this is 0 because you can't reach any winning position. Nine. How much time do we have? Because if we can speed this up, 1 second. Huh. Yeah, you don't need this you don't need this to be the whole way. You can do over 2. So initially, yeah, if left is greater than right, then you break. We probably don't need this. We probably can just do a Boolean array, right? Boolean array, reachable, new Boolean array, 20. And then reachable at this equals true, maybe 32. Well, reachable at max. Very speedy. Max is 9. So we can make this probably 16. Okay. What about 500,000? One. Yeah, so we need some sort of hash of an array to see if it's equal. We're a little too slow, but maybe you only have to check like 10 things or something. We'll probably hack it. Yeah, we can probably choose this one. We can probably choose this one. There probably aren't that many equal to 9, I would imagine. much time do we have? 40 minutes? Yeah, we can probably get that. How my friends doing? Amanda's doing all right. Gotta love it. Yeah. Pretty solid, pretty solid. Not too different from what I'd expect, I guess. Yeah, okay. Okay. So let's get a hash, huh? Let's get the hack pack. And then let's get Harmeyer hash. Take this. Okay, so we don't need this probably. Well, let's just make this static and fix everything. Static, okay, and then we should be good there. And then what else? I think we're set, right? So that's it. Okay, so let's only do 100,000. It'll be faster. Okay, fbrute, we'll call this fbrute safe. And then Harmeyer hash test goes through Harmeyer hash. And then we can say, just do it at the end, I guess. For int I in A. We'll say test.add I plus 1. And then we'll say, or test.add. We just need this to be an int. Okay, what's wrong with that? Go. Alright, and then we're set here, okay, and then this out test.v1 plus test.v2, okay. Yeah, alright, so this is the cool. So this is 100K. Let's make it 10K because that'll be fast so we can test quickly. Gives us this, and we also need 500K. Okay. So then, what are we going to try? Just 1,000? Try it. I really hope my brute forcer wasn't wrong, because that would be disastrous. But it seems fine. The first couple numbers seem reasonable, so should be good there. Alright. Getting impatient. Time is ticking. We got like 30 minutes left, right? 35? 37. Get me my answer. Okay, well, I guess this is going. So, yeah, what can we try? We can do the first 1,000. We can do everything, and then maybe, yeah, maybe just, so this will be A, and then maybe we'll calculate some B here. We don't need this. Yeah, let's do 10,000, and let's make another B. Oops, okay, so, yeah, we'll have like static int array get real, and then some int size. All right, and this will return this part. So we can do this. Nope. We can do this. Where's get real? Get real. This, and then we can say int array a equals get real of 10,000. And then we'll say int array b equals get fake of 10,000. Now we need, this will be in B, okay. So now we need get fake. This needs to be size. Okay, and then we'll say, what's the easiest thing to do here? Get real. What do we do? Return. I'll return a. Return a. All right. Okay. So then here we need to say. Yeah, we want to say if it's. What is this? Is greater than 1,000, then just break. All right, let's count the mismatches then. Quite a few. That doesn't work. Yeah, that's like almost all of them. That's like 70%. All right. I plus, oh wait, OEIS, what about just OEIS? What? No way. No way. Really? Am I doing it wrong? How is this not a thing? 0, 1, 2. Okay, fine. We'll do this instead. Zero, 0, 5, 9, 15, 21. Wow, it's kind of weird. All right, what if we try this? Yeah, I still think we can choose this. Because I feel like it's random enough. There's no way this is, like, it's a mathematical property. You can't. So what do we do here? We can say, oh, maybe the problem is, like, we start, okay, yeah, let's count the frequency. 0 6s, okay. So they're about 200. So we can check some random positions maybe. All right. Interesting. Okay, so yeah, we can probably do some stuff with this. Then we can say like, yeah, pick some random things. 5 and 4. It's like reasonable. Yeah. Okay. So yeah. So 4 int. We should try random stuff. Six. And we'll say four int tries equals 0, tries less than 100, tries plus plus. This is fake, right? Okay. So int split equals random dot next int up to I minus 1. Have this like total misses counter, and then if answer at I is not equal to, oh, what have I done? Come back. Okay. Is not equal to 8i, then 8i equals answer at I, and total misses plus plus. So then we'll do fake and then pass in the real answer. And then we'll do this one, I guess. What does this give us? 76. 76. Let's go. All right. So then what is this? So get fake, so then this will be, oh wait, 76, but that's not really important, is it? We need 100,000. So it's 76, and then this is 700. What? Oh. Only 76 still, but they don't match. Why don't they match? They should match. Did they match before? Why don't they match? Just fake. What's this? Hmm? I should be literally copying this over. Oh, dang. %. It's not great. It's really not great. Still about 10%. Oh man, this is very bad. Yeah, it's kind of lame. What if we do just like 1,000? that's not good enough though, is it? It's not. Yeah, it's not gonna work. It's gonna be too slow. So the answer is never more than 9, huh? Seconds. How many misses? 88,000. Even if I can get these, it's still too much. Okay. 18 minutes. So I need some way of calculating these big grounding numbers. Do I need big grounding numbers? I do, right? Yeah, I do. Well, hang on. So how many big things were there? 14,000 of each. Okay, what about the 7, 8s, and 9s? Do they repeat? Interesting. Maybe, yeah, the 7, 8s, and 9s repeat. Okay, let's make this 10,000. Okay, so 7, 8s, and 9s don't repeat, but I wonder. So then we can do one of these, I guess. So then seven, 7, 8, 9, 7, 8, 9. Okay, all right. Wait, so 7 and 8 are always plus 2? 7, 8 plus 2? 7, 8 plus 2? Yeah. 7, 8, okay. So if 8i equals 8 and 8i minus 2 is not equal to 7, then row null. Okay, and 8i equals 7 and 8i plus 2 is not equal to 8. And I is not equal to the first one. What is that? The first 7 is okay. Where are we printing this other place? $33. Okay. All right. So this is always true. Very nice. Okay. Yeah. What about the 7s? What do you think the differences are? So int last equals 0. I plus space plus I minus last, and then last equals I. 34. Jesus. Okay, we get all the 30. We get all these for free. Okay, nice. Cool. All right. So 7s are 33 plus 33 plus 34 times n. What about everything else? Okay, yeah, what about... Oh wait, what if they just repeat every 34? If I is greater than 50, and I is not equal to, or and 8i is not equal to 8i minus 34, and 0 null. Okay. All right, fine. What about if it's equal to 8? I guess 8 will probably repeat too, right? So 8s are just 69 plus 34. 8s are 69 plus 34n. Okay. What about 9s? Minutes, oh boy. 9s are also repeatable. 9s are 86. Okay, so we can fill in the, yeah, we can fill in everything else. Okay, so yeah, okay, so we can do this, and we can say it's not equal to this, and 8i is not equal to 7, or 8 or 9. Okay, now how many misses do we get? Fake took 23, total misses 700. Really, so it's just missing all of them, okay. All right, we got 7, 8, 9. What about 5s? So we get 16, 15, 19, 1, 14, 19, 1, 14, 19, 1, 14, 19, 1. What about, okay, what is 14 plus 19 plus 1? Is it 34? 14 plus 19 plus 1. It's 34, my goodness. Okay. So we also get the 5s. So we literally get, yeah, okay. So we get 16, 31, 50, yeah. So we also get the 5s. So what about greater than 5? How many total misses? $200 of 10,000, or 100,000. $1,000, 10,000. $2,000. It's about 10,000. It's doable. Should we look at 4s? Maybe we look at 4s too. So do this to 10,000. Okay, that's true. What about greater than 3? Greater than 2? That was true. My goodness! Dang it! Okay. Alright. So we can solve this then. Alright. So F. Give me F. Alright, so then we need F brute. We need get real. Where is get real? Get real. Get real. Okay. We don't need this anymore. We just need F. Okay, so we get real. So we need static int array ants equals get real 1,000. Alright, int array. What is this? This is, what's it called? Nimber? Yeah, Nimber. Okay. Then we need, is it multi-test case or no? Problems. Calling game. It is, okay. Int t equals this. Okay, so then what do we have? We have n. Int n equals this. Array line equals this, int a count equals 0, b count equals 0 for char c in line. If c equals a, then a count plus plus, else b count plus plus. If a count is not equal to b count, if a count is greater than b count, then do this, otherwise do this, and then continue. What do we print here? So this is, it's not circular, right? In a row, okay. This is Alice, out Alice, otherwise we'll print Bob. Okay, this is next dot to char array. What do we have next? Now we need the groups. Yeah, so we take the same number of normal steps. We need the groups. Okay, so array list integer groups equals new array list, and then yeah, so 4 int. Okay, so I guess what do we need? Current size. Int cur size equals 0. 4 int I equals 0. I is less than D. That's two things. That's one move. Yeah. Okay. I is less than n, I plus plus. If a at I is equal to a at I minus 1, then first size plus plus. What if it's not? It's not. So then we're done. So then groups dot add first size, and first size equals 1. And add this at the end. All right. Int max equals 0. If max equals 0, do this. Otherwise, do this. So what if it's 0? So that means Alice goes first, right? So then sys out Bob. Otherwise, sys out Alice. All right, and then for I in groups, we'll say if I is greater than 1,000, yeah, then we need to go back. Okay, so, oh, we need to build this. Okay, so then int array number full equals new int array 5001. I equals 0, I is less than 1,000, plus plus. Number full at I equals number at I. How much time? 3 minutes, we can do it. All right. 4 and I equals 1,000. I is less than number full dot length plus plus number full at I equals number full at I minus 34. Okay. And then max XOR equals number full at I. Okay. Oh crap. Oh, R. Yeah, Alice is red. Okay. A equals 1, curve size equals 1. Bob, Bob, Bob. Bob, Bob. Oh, crap. Alice wins this. Crap. Groups. Groups are 1. No, they should be 1. Oh, if it's equal. So where's not equal? If it's not equal. Okay, Bob wins that. Yep. It is Bob, right? It is Bob. Okay. So this copy Bob, Bob, a bunch of Alice's, 2 Bobs. Oh my goodness. Yeah. Okay, submit. Oh my goodness, oh my goodness. Oh my goodness. Where's OBS? Is OBS still alive? We are? Okay. Alright, come on. Come on. Let's go! Let's go! Let's go! Dude! Ah, the number 34! Oh my goodness. Whew. Wow. Dude, my heart is pounding. There's under a minute to go. Whoa, that was so clutch. Oh my goodness. Whoa, man. Whew. Whew. Wow, that was stressful. Oh my goodness. Oh. That's what makes competitive programming fun right there. Oh my goodness. Wow. I cannot believe I got that. I figured it out with like 15 minutes left or something. This is going to be an exciting part of the video to rewatch, let me tell you. Oh my goodness. Wow. That was fun. I am so happy I got that. How much time did I have left? I had 49 seconds left. I submitted it without running samples. I was like worried it would TLE. Maybe I didn't need to be worried about that, but like I didn't read how many test cases there were. Oh my god, we got the green lights. Man, 10 of the 4 test cases, so I probably would have been fine. I probably didn't need to do the last minute change, but still. Wow. Oh my goodness. That's insane. Insane. I tied this guy. Yeah, okay, what was my performance? 2660, so I'm performing at IGM level. I gained some more points. Let's go. Let's go. Man, that was fun. Wow. Wow. Alright. That was awesome. How did my friends do? My manager got A, B, and C. Not bad. It's probably still good. I mean, if you're cyan, that'll probably move you up. We got more friends here. This is horrendous. Andy, come on, this is horrendous. He must have started late or something. 40 minutes for A? Did he get wrong answers on A or something? Anderson. Maybe he started late. I don't know. That's kind of embarrassing. You can do better than that. Anderson competed with me. He used to be red, I think. He was like one of the 3 people ever from UCF to get red. Yeah, he got red. I think only 3 people ever from UCF have ever gotten red. Me, him, and then one guy from a while ago. Yeah, so if you're red, you should be getting one of these, I think. Man, that is fun. Okay, anyway. Yeah, I guess talk about solutions, huh? Ugh. Wow. Okay, I accidentally opened up VS Code, so we'll close that. Wow. Okay, alright. Fun contest, let me just say that. That was fun. I thoroughly enjoyed it. This one was a bit odd. Yeah, I guess it wasn't bad. Not terrible. Bit hard to implement. This one was easy to implement, but just requires this insane observation. Taurus got it pretty quick. Yeah. Very fun. Very fun. Okay, yeah, let's talk about solutions. My heart rate has calmed down to like a human level now. Okay, problem A. 2 0 1 sequences. So in this problem, you have two operations you can do. If you can look at the first two characters. So you've got like two sequences of zeros and ones. First one, maybe it's this. The second one is this. And you want to turn the first one into this. And you can delete characters in the first one in order to do that. The two operations you can do are you can take the first two characters and you can delete the first one you can delete the second, I don't know, whatever. So yeah, I'll just talk about what they actually mean. You can replace them, if they're the same, you can replace these two characters with one copy of what they are. If they're different, you can replace the first character with either a 0 or a 1. So the idea here is that you can only change like the first two characters. Those are the only things you can choose from. And then that will only affect the first character in the final array. So all of these 5 characters will contribute toward the first character, and then the suffix has to be the same. And the question is, can you make this equal to that doing so? And really the question is like, is there any character in the first prefix that would match this first character? Because once we get a 1, we're going to continue picking the 1 for everything after it, right? So the question is just, is there, like, this is a 1, so we're looking for, is there a 1 in this first group? And there is. For this part, we want to say, is there a 0 in this first group? Because there's a 0 here, and there is, so it's also possible. So these two are yes. And then in the third case, these suffixes have to match, right? So we want to know, is there a 1? Sorry, this suffix has to match this. So we want to know, is there a 1 in this group? And there isn't. Also, if the suffixes don't match, like in this case, this suffix has to match this suffix, and they don't match. So the answer is no. Okay. So to implement that, it's a little tricky for problem A, I'd say, but it's not too bad. The idea is that we read in our input, so n is the length of the first array, n2 is the length of the second array, and then I have a and b. We're going to read through everything in the second array except for the first character, and we're going to do that backwards. So the number of things that there are except for the first character is n2 minus 1. So we have an I, so if n2 is like 10, we want I to go from 0 to 8, right? We want it to be 0 to 8 inclusive, because index 9 will be the last index. So we want to see if the last that many things match, right? So if they all match, then we're good. We print, if any of them don't match, it's impossible, because we can only affect the first character with our first prefix. So the rest of them are going to stay the same. So it's impossible otherwise. But if they do match, then we need to check, is there a first character we can use in the first group? So we'll consider the first group, and we look through it, and we want to see, is there any character that works? And if there is, the answer is yes. Otherwise, the answer is no. And that's the entirety of the problem. Yes, that's problem A. Awesome. Let's clean this up a bit, and then we will pick problem B. We'll look at problem B. Luke the foodie. All right, so here we go. You got this stuff happening. What is the idea? Yeah. So you have a bunch of piles of food, and you're going to eat the piles from the beginning to end, and you can eat them if you are at most k away from the value in that array, basically. So here, you could pick your value of the array equal to 6, and then you can eat the entire array, because these are all 6 plus or minus 3, right? They're all between 3 and 9. In this case, though, you can't do that, right? If you pick a value of 3, or if you pick a value of 6, you can reach the 3, but you can't reach the 10, because 10 is 4 more than 6. It's not within the plus or minus 3 range that you're allowed. So you can pick 6, but then after that, you have to change it to 7. And you can, with 7, you can get 10, 9, 8, and 7. And that's the idea. So that's the problem anyway. So the question is, like, what is the fewest number of changes you have to make to your food value in order to eat the entire array? In this case, the answer would be 1. In this case, the answer would be 0. And then here's a much longer case. I won't go through it because it's so long, but the answer can be as big as n, right? You can imagine it goes like 1,000, 0, 1,000, 0, 1,000, 0, and your range is only like 1 big. So you have to keep changing it to like 1,000, then to 0, then to 1,000, then to 0. Okay, so how do you do this? Well, the tricky part so far, and this is like what I think of intuitively here, the tricky part is that when they ask you to change your food value, you don't know what you're changing it to. You have to change it to something in the right range, but it's not obvious immediately what thing you should pick. Now for the first number, it doesn't matter. You can pick anything in the range. But later on, it might, like maybe you have to pick something bigger than the first number because an element later is even bigger than that, right? And you have to like split the difference. So for this instance, like for this first number, we don't know what we want to start with. Maybe we want to start with 3, maybe we want to start with 0, maybe we want to start with 6. It turns out 5 or 6 are the right answers because this 8 will matter. But the 8 might be really far down on in the array, so you might not see it. So the trick here is we're not actually going to make the decision until we're forced to, right? So we'll make a decision of what number we would have picked in the past based on the things we've seen after it. And then once we've seen, okay, no matter what we do, we can't possibly satisfy this entire array, this entire range, we'll satisfy the parts in the beginning of the range, and then we'll pick a number that satisfies those, and then we'll start again with this new number, and we won't pick a number for that yet until we need to, or we hit the end of the array. So here's how you implement that. The idea is it's actually really simple. We'll store n and k. These are the length of the number of food piles, and then the allowable range, right? Plus or minus k. And then you read in what the food pile values are. Voice crack, what they are. So then we're going to go from, for each element in the array, and we're going to store like of the range that we're considering, what's the smallest and the biggest thing in that range. So as an example, yeah, let's look at this range here. So we'll start, well, let's say it's actually this, right? And let's say k equals 3. So you're allowed plus or minus 3. So initially, the range is just, we'll say it's just 2. It's 2 to 2, because we're considering just this element. Then we'll expand our range to this. So now the range is 2 to 3. Well, 2 to 3 we can satisfy, right? If we pick the number 5, that would get 2 and 3. Or we could pick 3. It would handle both of these, because both of those would be 5 plus or minus 3. Within that range. So it's fine. So we can handle this range in all one thing. Okay, now we'll try this 10. We can try the 10. But the problem is now this range is too big, right? Now the range goes from 2 to 10. And if you have plus or minus 3, even if you split the difference, pick right in the middle, what is that? 6? You pick 6. 6 is too far away from 2, and it's also too far away from 10. So it doesn't work on both accounts. So yeah, 6 is just, it doesn't work. So you'd have to pick, the biggest thing you could pick would be 2 plus 3, which is 5. But that's 5 away from 10, not 3 away from 10. So what that means is you have to split. You have to create a split point here. So you've got a split point. And we'll pick a number that satisfies 2 and 3. We don't actually have to pick it, but if we wanted to, we could pick the min plus 3, right? So that would be 5. That'd be a good number we could pick. And then we'll start a new range here at 10. So now our range will be 10 to 10. And then we'll look at this 9. All right, so we take the 9, our range will be from 9 to 10. All right, then we take an 8, so our range will be from 8 to 10. We take a 7, it'll be from 7 to 10. So we have 2 ranges. The first one goes from 2 to 3. The next one goes from 7 to 10. That's the idea. I will show you the code in 5 seconds. Give me a quick countdown here while I change the battery on my camera. 5. 4, 3, 2, 1, 0. I think we're good. Are we good? Maybe. Hello? Hello? All right, cool. That's problem B. This one should have a bit more battery, I think. Okay, so yeah, sorry about the camera issues today. Cool, that's solution to problem B. Yeah, oh, I guess, yeah, you store the min and the max. Every time you see a new number, you update the min and the max, and then if it's ever bigger than k, you reset your min and max to this element, and then you increment the number of splits. And then put the answer at the end. That's B. Okay, cool, well done. Let's take problem C, virus. We have n houses, and oh, this one like caught me up for a minute. The first thing I tried here was wrong. It's a bit tricky. So we have a bunch of houses in a circle. Circle is important, a bit tricky, but we can handle it. So we have n houses in a circle, and every day, all of the infected ones will spread to the neighboring houses. And also, before every day happens, every morning, good morning, we can pick a house and like make it safe so that it'll never get sick. And that's the idea. Okay, so that's the problem. How do you solve it? So, yeah, it turns out you want to, every turn, you want to place your stoppers adjacent to some virus that's spreading so that it does as much as possible. And it makes sense for us to try and stop the biggest ranges of unprotected houses in the beginning, at first. The logic behind why we want to do that is that there might be smaller ranges where over time they'll all get infected and then the virus will stop spreading in that range, right? So you can imagine for instance, pretend this was circular. So we have a big circle of these and then the first one hits the last one, right? If we have a virus at these two X positions, the first turn, sure, we could save this if we wanted to, but if we saved this spot here and this spot here somehow, we would protect all of these things. But if it takes a couple turns, no matter how many turns we don't protect the stuff in the middle, only one thing will get infected. So it's not very helpful for us to spend our turns on smaller ranges, because it's possible we could just lose all of those houses and then it's fine. Or it's the least cost we would have to pay. So yeah, that's the idea. That's the important part is we want to prioritize the biggest ranges because those are the ones that will matter for the longest. The smallest ones, it'll be painful at first, but then eventually we'll have endured all of the pain and then everyone will be sick and it's fine, right? It doesn't matter what we do at that point. So yeah, that's the intuition behind why we should prioritize the biggest ranges. And the idea is every time you have a house that's a virus, you can split the range up, or you can split the thing up. So we have something like this, and these two are connected, right? The first and last, so I'll do this. So we have a range of size 1 and a range of size 5. That's what we've got. Now, every turn, what will happen is the virus will spread on both ends of this. So it'll spread to here and here. And then also, it'll spread on both ends of this. So it'll spread left 1. I mean, this will already be full, but it would, if this had two things, it would take up both of these on one turn, and it'll also take the first and last of each of these. So for every range of healthy houses, we lose the first and last every turn. So what that means is we can just sort these groups by their size, right? So we get something like this. And the first turn, we can save both of these by only losing one, right? So we would save this, we'd lose this, and then we'd save this. So we would save 4 of these people, these 4 people. And then the next turn, if this were some range, maybe let's give it 5 as well, right? So we've already lost this one here and this one here because we were busy working on this group earlier. Now we can save this here, so we can save this, and we'll lose this when we save it, and we can save this, so we can save 2. And now in future groups, the virus, we've spent 2 turns here and 2 turns here, so the virus has spread 4 from each side. So instead of this having a width of 5, it would have a width of -3, which is equivalent to a width of 0, if that makes sense. So yeah, it's spread 4 from the left, 4 from the right, so it's everybody here is dead. But in total, we can save these 4 people. Oops. We can save these 4 people, and then we can save these 2 people. And we do that with 4 moves. Okay, that's the idea. So yeah, the important part here, the ideas for the solution are we want to keep track of the gap ranges, right? The ranges of healthy houses. And then we want to save the biggest ones first. And then just do this in a fast way. So yeah, do it in linear time is the idea, in order n. So how do we do this? We get the houses, sort them in order, circularly, and then we get all of the gaps between the houses. The first gap is a bit tricky because it's the first one minus the last one plus n. Or I guess, sorry, minus the last one minus n, right? Because you want to wrap this one around. So this will give us the gap between the first house and the last house. And then we also need the gaps between all the other houses, and that's easy. It's just the subtraction. You also have to subtract 1 here because if you have a house if house 2 is sick and house 4 is sick, 2 minus 4 is 2, but really only the house between them is safe, right? Because both endpoints are sick, so you need to subtract 1. And that'll give you the number of safe houses. Yeah, okay. So then I sort the gaps by their size, and this gives like the most important gaps at the end. So those are the ones we'll save first. So then I go backwards through this range of gaps, and I start with the biggest ones. First of all, I subtract out the number of things the virus would have eaten. So I would have infected. The zombies would have eaten. So yeah, this is a variable I keep track of, and this is like for everything after me in the array, how much should I subtract from it? This allows me to not actually go and subtract from all of those elements, because if I did that, then for every element, I would look at every other element. Right? So for all 100,000 elements, I look at 100,000 elements. The runtime will be 100,000 times 100,000, which would be 10 to the 10, which is too big. A computer can only do about 10 to the 8 things a second, so that takes 100 seconds. So that'd be too slow, that'd TLE. So instead, what is this? Yeah, I go through the houses, or the ranges from biggest to smallest. If the range only has 1 or 2 things, then I can only save one of them. So I save one of them, and I do it in one turn. So the virus will expand on each side of all future ranges, but just once. Otherwise, I can save all but one of them. So I save the first one, and then I save the second last one. So I lose one of the guys in the range, but I get the rest. And this takes 2 turns. So then I lose 4 things from all the other ranges, because the virus moves in twice from each end. And then that's the answer. Oh, sorry. Yeah, the answer, I guess, is the number of people I don't save is how many get infected. So, yeah. There you go. That's problem C. All right, problem D. Magical array. Eric has an array B of length m, and then he generates n additional arrays, each of length m, from the array in the following way. So in one of the arrays, it's special. So in the special array, what he does is, like, when he does an operation, he picks an element, he subtracts, or he subtracts one from, he picks 2 elements. Yeah, okay. So in a normal array, he'll pick 2 elements, he'll subtract one from the one before the first. No, he'll subtract one from both, and he'll add one to the one before the first, and also to the one after the second. So like he'll take, if you imagine like a bunch of stacks, and the AI values of the height, he'll take 2 rocks, and he'll move them out, each by 1. So that's the first operation. The second operation happens only on the special array. So there's only one array that this happens on. And in this one, he'll take the 2 rocks, he'll move the first one left by 1. I have to go backwards. Okay, he'll move the first one left by 1. He'll move the other one right by 2. So instead of it being balanced, it's imbalanced, because this one moves farther. The thing to notice here is if you imagine the center of mass of all of these stones. In the first operation, the center of mass doesn't change. It would be balanced over like the same point, kind of. Because when you move one to the left, you move the other one to the right. So the average position of all the stones stays the same. In the second operation, that's not the case. Anytime you do operation 2, the board will move over by 1. Right? The center of mass will move over by 1. So the thing that you do operation 2 for, that will have a different center of mass than all of the other ones, because they started with the same center of mass, and now it'll be different anytime you do operation 2. And they promise you'll do operation 2 at least once. Somewhere they do. Yeah, it's guaranteed. Oh, right here. Yes. Okay, yeah, so this is true as well. So, yeah, you'll do, on the non-special array, you do everything at least once, and then on the special array, you also do everything at least once. Okay. Yes. So that's the idea. You have to detect which of these arrays has a different center of mass than the rest. And I can show you how to do that. So the center of mass is really just, I store it in this values array. This is just all of the arrays. So the first index is which array, the second index is what what position in the array. Yeah, so I read in all the arrays here. And then the values, these are the center of mass of each of the things. So the center of mass is just the index times the value, right? So I just add these up for all of the positions, and I know the sum across the array will be the same, right? You don't ever remove a stone or add a stone, you just like move them. So I don't need to divide by the number of stones or anything to get the average position. My answers, like all of these will just be off by a certain factor of whatever. Okay, so then I can figure out what the answer is by just finding the one array that has a bigger center of mass than the rest of them. So I start at, like initially my answer is position 0, but then if any of the other arrays have a center of mass bigger than position 0's, then that is the special array. And then I also store like one thing that's not special. And then my answer, like the number of times you've used operation 2, is the number of times that the center of mass is off, right? The number of, like the center of mass of the special one minus the center of mass of the other ones. Because every time we do this operation, the delta in center of mass is changed by 1, or the delta increases by 1. So yeah, that's the idea. Yeah, the best way of like actually understanding this is thinking of piles of stones and what happens to them. And then the center of mass part. Okay. Yes, all right, there we go. That's problem D. Okay, problem E, count seconds. Yeah, this one is like kind of confusing, but I'll explain it anyway. So you've got some array, no, JK, you've got some directed acyclic graph. And this is just a graph that's directed, so each of the edges go in only one direction, and there are no cycles. So you can't ever start at some node, take some edges, get back to the same node you started with. Okay, so then initially all of the nodes have like some tokens on them, and they can have quite a few tokens on them. They can have up to like 1 billion tokens. And what will happen is every turn, for every node that has tokens, you'll remove one token, and you'll give a free bonus token to all of the things that it has an edge to, right? So you might remove one token and create 2 new tokens. So the number of tokens doesn't necessarily stay the same. And the question is, when is the time the last token is removed from the board? Now, there's an additional constraint on the graph, which is there is exactly one node that doesn't have any outgoing edges. What this means is the last token will be at that node. Right? We know when which node the last token will be removed from. And that makes things so much easier. And I'll talk about why in just a minute. So yeah, don't forget this line of the question. All right, so how do we do this? Well, there are a couple observations. The first one is that when you have a bunch of tokens on a node, the first one will be removed at time 0 or whatever, and then they'll be removed for a continuous range of time. Right? So it's going to be like remove a token, remove a token, move a token, move a token, move a token, and then, oh, you're out of tokens, you're done. So we're going to store for each node, there are only 1,000 nodes, but for each node we're going to store the ranges of time that this kind of thing happens. And then what happens after that is like, we're going to remove these nodes for like a given range of time, and then we run out, and then maybe later on we start getting tokens from another node. So you can imagine you have like a really long chain, right? And then the first one starts giving away its tokens, it runs out. And then finally, after like 20 turns, the tokens from really far away end up reaching you. All right, so now you start having more tokens again. And then here you'll start giving them again. But again, it's for a continuous range. And then you might run out, and then later on you'll get new range. The important thing is the time that you start, the start times of each of these ranges, the start times are never very big. Because the only time the start time would be like big is if there's a path that the other group has to take to get to you. So that start path, it can't be longer than going through each node once. So the start path is at most length n, which means the start elements are at most, or like the start of each of these ranges are at most n. Now the n's can be gigantic. The n's can be like 2 to the 1,000 or so, like 2 to the 500. Which is way bigger of a number than you can store in any like int, long, anything like that. So you have to be careful with the end points, but with the start points you can be less careful. You also have to be a little careful because the endpoints, you want to store them under mod, right? And this is like, even if you're good at competitive programming, you have to be really careful here because you store the endpoints under mod, but it matters whether two ranges intersect or not. Because if they don't intersect, you can't add them together. But if they do intersect, you can. So it's important like what the ranges actually are. And it's also important what they are under mod. What I mean by this is like something might be 3 mod this giant number. But it matters whether it's a giant number plus 3 or whether it's just 3. Because if it's a giant number plus 3, it will definitely intersect the next range. Because the ranges all start in the like order of 1,000, right? So if you have a giant number, it'll intersect the next one. But if it's only 3, then you can have one that starts at 5 and one that starts at 15, and these two ranges are separate. So the distinction between those two is important, which means we have to be very careful how we handle our mods for this problem, differently from how you normally can handle mods. Usually, like, you just take the value under mod, it doesn't matter how many times you've modded it, it's fine. But here, whether you've modded it or not is important. So, like, what I do is I store the value, if it's under the mod, it means it hasn't been modded. But if it's between the mod and 2 times the mod, in particular the mod and the mod minus 1 plus the mod, by the mod I just mean this number. If it's in that range, between the mod and less than 2 times the mod, then that means it has been modded. And I just store like the value under mod. And then at the end, I mod the whole thing, so I give the right answer. Yeah. Okay. So there are a couple implementation details that are a bit tricky here. The first one, I accidentally typed some, what? Oh, E2. Yeah. So, yeah. Some implementation details here that are a bit tricky are like, how do I do this? I'll just talk about the whole thing and then I'll mention the tricky parts when we get there. So first I read in all the input and then I store the in degree of each node. And this is useful because then I'll know, like I'll be able to do my top sort with this in degree counter. Okay, then I'll do a BFS and this will be like a top sort BFS. So I'll store the in degrees like of each node and yeah, like this is like top sort BFS. So this gets me like the way of removing nodes so that you never remove a node that has an edge to it. And this way I'll process the nodes in this order and it'll be very nice for me. Okay. Yeah, that's what this part's doing. This gets the top sort order. Okay. Then for each node in the top sort order, what I'll do is first I'll compress all the ranges, and I'll talk about what that means in just a minute, but I'll compress the ranges, and then I'll give these compressed ranges to everybody else. So the important thing here is after I've compressed the ranges, I will have at most n ranges to give. And the reason that's true is the starting points can have at most n different values. So there will be at most n ranges that I give. There won't be like 2 to the n or n squared or anything. So the final runtime will just be n squared log n. It's a bit scary, but in practice it's fine because I do have to sort these to do the compression. And I'll try and give them to all my neighbors. The try and give part is really easy. Basically, I just go through all of my gifts, which are like my ranges. I call them gifts for whatever reason because you're giving them to people. But yeah, I go through all of my gifts and then I just take my gift. It'll take one more starting time because it has to take one turn to get from me to him. And then I'll give him a copy of the gift. So this is try to give to. This is easy. The compressed gifts part is a bit more tricky. So the reason you have to compress them is like you might have 2 gifts that kind of overlap, right? Like you might give one gift in this time, one gift to this time. If this happens, you have to move this gift to the farther time. And you don't want like 2 different gifts here because then the number of gifts can be quite big. So instead, you want to just like combine these into one range that's like this, right? So it's this and this, you combine it into this. And that's what this is doing. The start time is just the minimum of the 2, and the size is the sum of the sizes, which is intuitive enough. However, it's a bit tricky insofar as like you want to be somewhat fast here because you can have n gifts and you don't want to do an n squared. Maybe it doesn't matter. But yeah, I think you want to be fast. So I sort them and then do them like in order of start time. I sort them by start time, and then I go through order of start time. And if like two adjacent ones overlap, then I combine them. Or if they don't overlap, then I add the previous one, and I know nothing will ever intersect that because the start time is like the new cutoff. Okay. Yeah, I think that's enough. The only tricky part is this add size function. So I can't just do like the size plus equals the size of the other thing. And the reason is that could overflow my mod and then get to a really small number. And then it would look like I might have like a giant size, right? And then I add another giant size and I get like really tiny size. And then it doesn't intersect this next one, but it should. So these don't get combined. So instead, yeah, I do this thing where I store the amount as something between mod and 2 times mod, if it's been modded before. So that's what's going on here. Like if it's bigger than mod, then I mod it, and then I add the mod back. So yeah, this is what's going on. Okay. And I think that's basically all the important parts. Yeah, I check if they intersect, but this is easy enough. Yeah, so I think that's the important part here. So the reason this is n squared is like, I do my top sort, that's order n, that's fast. Then I am passing gifts between things, but from each thing, I only pass order n gifts to the next guy. So in total, a given element, it'll get at most the number of its in degree times order n. So the total number of gifts that are passed are the total number of edges times n. So it's like, it's safe there. And then, yeah, I compress your gifts before I tell you to give them to anybody else. So across each edge, I give at most n gifts. Yeah, and then the answer is just like for the last node in the top sort, which is just the node that everything goes to, I just print his last thing. Now, this would be really hard if it wasn't just this one node. And the reason is we would have to be comparing these gigantic numbers and getting their answer under mod, which is like a really hard thing to do, right? If you store the gigantic numbers, you're gonna TLE. So you'd have to store like some compressed version of them, maybe like their decimal representation in a float. But floats aren't like big enough where we could actually do this. So the observation has to be the last thing. Instead of like actually trying to compare these times, we know the last time is just gonna be that one node that's like the end, and it's gonna be the one with the last start time. And that's the only thing we have to look at. So that lets us actually calculate the answer. Yeah, okay. He has been explained. I think that's all the parts I want to talk about. Okay, good. Yeah, we have, oh, I guess just this. Yeah, I don't know how to do these ones, so just F. Okay, let's talk about F. F is very fun problem. Yeah, I really enjoyed it. Well, okay, it's fun, and also, if you don't solve it, it's a little sketchy. Because there's just this magic thing, which is totally unpredictable, but just so happens to be true. So here's the idea, or here's the problem. You have this array of like blues and reds, and every turn, what a player will do, so Alice uses reds, Bob uses blue, and Alice will pick a red and something next to it. And she'll paint both of those white. She can pick a red and a white, that's allowed. She's allowed to pick a red and a white. And then she'll paint both of them white. Bob will pick a blue and something next to it. So he can pick a blue and a red, or a blue and a white, or a blue and a blue. Yeah, exactly. And then the winner is the person who moves last, right? If you can't move, you lose. So, okay, couple observations here. First, Alice likes spaces that are red. Because if there's a red space, that means she can make another move. Bob likes spaces that are blue. Now, Bob obviously wants to remove spaces that are red, and Alice wants to remove spaces that are blue, because Alice wants Bob to have fewer turns, Bob wants Alice to have fewer turns. Also, since Alice likes spaces that are red, it turns out it's never in Alice's best interest to remove 2 spaces that are red. Alice is only going to remove 1 red space each turn. There's one exception, which is the board is entirely red, but we'll pretend in that case, she can just remove 1 red, because, like, why not? Yeah, so, because she'll win anyway, right? She'll make some move, and Bob has no blues, so he'll lose. So, yeah, the idea is, like, we we'll say Alice removes one red each turn, Bob removes one blue each turn. If there aren't reds and blues next to each other, Alice will remove a red and a white. Otherwise, she'll remove a red and a blue. And then same thing with Bob. He'll remove a red and a blue if he can. Otherwise, he'll remove a blue and a white. Unless the board is all blues, in which case Alice would have lost on her first turn anyway. Okay, so clearly we know what people are going to do each turn. We know Alice will remove a red or a red and a blue if she can, and Bob will remove a blue or a blue and a red if he can. So it seems like it's an easy problem, right? Well, the hard part is like, which red and blue do you remove? That's the tricky part of the problem. Which red and blue do you remove? As an example, let's look at this case here. Well, this case doesn't matter. Let's look at the case where it's... Let's look at red, blue, this case. So if you are... Let's say you're Alice, you're removing reds, right? You go first, it's your turn. You have two decisions. The first decision is you could remove these two. You could also remove these two, right? Or you can remove these two. The first two and the last two are the same, so it doesn't matter. But the question is, do you want to remove the middle two or the left two? And this decision is very important, right? If you make the wrong choice here, you lose the game, and you could win the game. So in particular, right, if you remove these two, then Bob has to remove his blue and the white, right? So let's say you remove the middle two. Then you have two whites in the middle. So Bob removes his blue here, and he changes these last two to white. Now it's your turn, you change these to white, and now it's Bob's turn and he loses. So if you remove the middle two, you win. But if you remove the first two, you lose, right? So if you remove these two, now it's Bob's turn, he removes these two, and now it's your turn and you have nothing to remove, so you lose. So the important part is like, even if it's a tie for the number of reds and blues, you still might win or lose depending on like how this board is structured. So you got to be careful here. Yes, okay. So yeah, the first thing I mentioned, like if it's a tie, you have to be careful. What if it's not a tie? Well, if there are more reds than blues, right? If we have like a bunch of reds and a couple blues, then like Alice is gonna win no matter what. You can prove it, but basically like you remove one R each turn, you remove one blue each turn. Even if the first and last thing you remove is an R, then you're gonna have like it's gonna be Bob's turn. He'll have to remove a blue, and he won't be able to. And the reds will be able to satisfy that, so you'll be fine. Same thing if there are too many blues. Like if there are more blues than reds, then Bob will win no matter what, right? Because Alice will remove one red each turn, Bob will remove one blue each turn, and then it'll be over. The reason that like Alice can't remove a red and a blue, and Bob removes just a blue, is like if there are reds and blues together, then Bob will remove them too. So it'll be red, blue, red, blue, red, blue, red, blue, red, blue. Even if Alice gets the last one, which she wants, then Bob will still be able to remove blue, red, blue, red, blue, red, blue, red, and then Alice will run out. So if you have more blues, Bob wins. If you have more reds, Alice wins. If it's a tie, that's when the problem gets really hard. Okay. All right, so that's the first part. Understand that. Pause, maybe rewatch what I've explained. Understand that. But you have to understand if there are more reds or more blues, the game is over. The hard part is when it's the same. Okay, what do we do when it's the same? So let's consider just like what this thing can look like. So if we have some reds here, and then we have some blues, and then we have like some reds here, and then we have some blues here like this. So in this case, the important part is we've got here, we have like this red-blue pair. We also have red-blue pair here, and we have one here. Now we know every person wants to remove a red-blue pair if they can. And in this case, there are 3 pairs that will be removed. So 3 turns are going to be spent removing red-blue pairs. And then after all the pairs have been removed, people will remove just reds or blues. So the winner is actually the person who removes the last red-blue pair, because they will be the person who goes second, right? If you have a bunch of reds and a bunch of blues and they're separate, then the person who goes, and you have the same number of reds and blues, the person who goes first is going to lose. because they're going to run out first, right? It's like 1, 1, 2, 2, 3, 3. Oh, there is no fourth one, so this person loses. This person would lose, but it's not his turn. Okay, so you want to be the person who removes the last red-blue pair. That makes you win. So you have this pair here, and this pair here. There are 3. Alice removes the first one, and 3 is odd, which means Alice wins. If we had this case here, in this case, Alice removes this one, Bob removes this one, and then it's over. So Alice wins. So it's pretty easy, right? Just count the number of pairs, and then you're done. Check the value of mine too. No, it's actually much more difficult. So consider this case. So here we have reds, reds, and blues. So we have 1 range here, 1 range here, 1 range here. That's 3 ranges. 3 is odd. That means Alice will remove the last one. She'll win. Well, yes. Well, actually, no. Yeah, no, Alice will lose. Because this range and this range overlap. So if someone removes this R, here you've got like technically like 2 red-blue pairs, but they use the same R. So really this is only like 1 turn, right? So really there are 2 turns. Alice will remove one of these, Bob will remove the other, and then after those things happen, there won't be anything left to remove. So Bob will actually win this. Because they're the same number of R's and B's. No, JK, there aren't. Here, okay. Alice wins this one. Sorry, Bob wins this one. Because they're the same number of R's and B's, and if you look at the red-blue pairs, during 2 turns, a red-blue pair will be removed. So Alice's turn, she'll remove one, Bob will remove one, and now Bob removed the last RB pair, so Bob wins. Okay. All right. So that's an example of why it's slightly less intuitive. Let's look at, so in this case you had this one red, and then you had some blues here. But you could have like a red, a blue, another red, and then another blue. Some blues over here, right? And you imagine like the reds and blues line up. But here you have this longer chain, right? This is a chain of like 1, 2, 3, 4, 5 things. You got a 5 long chain where it's alternating. And some interesting things can happen here. Like you could remove these 2. In that case, that leaves you with a 3 chain. Or you could remove these 2, and that leaves you with a 1 chain and a 2 chain. So maybe those are the same. Okay, maybe that's not interesting, but maybe you have like some 4s here, right? So here, in this case, you've got 4 things. You've got some interesting decisions you can make. Like, you can remove the middle 2, and then there are no more red blues to remove here. Or you can remove these 2, in which case you still have a red blue to remove. So you get these interesting decisions when you have like alternating R's and B's, just like we saw up here. Yeah, so here's the solution idea. Anytime you have 2 or more B's in a row, so we're going to assume this is equal, and we're only going to consider the red-blue pairs part here. So anytime you have like 2 or more B's in a row, it makes like a separate thing, right? So here we have a red and a blue, and then we have a bunch of B's in a row, but those won't interact with each other. So we have like a divider here. And now we have like a B, an R, a B, an R, and then we have 2 R's in a row. So this makes another divider, right? So we've got these like groups of things. And for each of these things, they're like its own, we'll call it its own game, right? We have its own board, and every turn what a player does is they pick a range that they're interested in, and they'll do something with it. So in this case, you might remove this pair, so that'll split this up here. So now we have a red, blue, and then 2 things on its own. Or you might choose these 2, right? And now you go like this. So now you have an empty pile, you've got these red, blue, and this red, blue. And if you're familiar with game theory, you notice this looks a lot like NIM, right? We have, in NIM, I won't explain what NIM is here because it's too hard. If you're not familiar with NIM, you're not going to be solving this problem. But in NIM, you have like a bunch of piles. You pick a pile and you make a move on that pile. So what we just need to do is we need to turn each of these things into an equivalent NIM pile using running numbers. There's a lot of new stuff there. So if you're not familiar with that, you got to go learn Gruddy numbers. It's too long to explain here. But you want to turn each of these into a NIM pile. Now the question that remains, the only part that's left, is like if we can turn each of these into a NIM pile, then the answer is just the answer for NIM, right? So we just take the XOR of all of the Grundy numbers, and that's the answer. But the question still is, how do we turn each of these into a NIM pile? Well, we use the classic Grundy number trick, which is we're interested in the MEX. So we want the minimum excludant, the minimum NIM pile this pile can't reach. So we're gonna look at all of the moves we can make here, and we're gonna see if you turn this into a nim pile, what nim piles can this one reach? You look at all of them, and you say, what's the smallest nim pile we can't reach? And that's gonna be our nim pile, because that's how nim works effectively. So this one, this 4, well, this one can reach a couple piles. It can reach, if we have RB, RB, this can reach, we can delete these first two, so it can reach this pile. It can reach this pile, one R and then another B, so we'll take these two XOR. Both of these are empty, right? These are equivalent empty piles. And it can reach like empty RB. So this is like another 1. So this can reach a nim pile of value 1 and a value 0. This is the same as a nim pile of value 2. Sorry, value 3. Nope, a value 2. It can reach a 1, it can reach a 0, so it's 2, right? The minimum, the max of 0 and 1 is 2. 2 is the smallest thing that's not in the 0, 1 set. Yeah, I know this is advanced. It's just kind of an advanced topic. I know. I'm sorry I'm losing people, but it's a hard problem. If you don't have game theory, you can't solve it. Yeah. Okay. So then, we just need to find the value of each of these piles. Well, that's easy enough, but the problem is that these piles can be size 500,000. We have piles of size 500,000, but we have to calculate them, and calculating it takes n squared. So the solution is just notice that every 34, it repeats. So if you have a group of size 34, and then you have a group of size another 34, after like 90 moves, they start repeating. Somehow. And you just have to notice this. You have to write a brute force and notice it. And that's the only way of solving the problem. So, yeah, I can show you what my brute force is. Here's my brute force. I have some size, and then I store the grunny numbers in this array. And then I store the max answer just for like seeing how big the answer gets. It only gets up to 9, in case you're wondering. And it never hits 6, just coincidentally. So then I just literally do it. I try all the split points, and then I see what you can reach, and I store this in my reachable array of size 16, and then the max is the smallest thing you can't reach. So yeah, it turns out this repeats. Turns out it repeats every 34. So I do this brute force thing, and then yeah, where do I do it? I don't know. Somewhere. After you do 1,000 of these, it repeats every 34. That's the important part. Blah, blah, blah. Doesn't matter. Yeah, so it repeats every 34, which means you only have to calculate the first 1,000 in n squared, and then for everything else, you can just look 34 back. You get the real array. Yeah, so that's the idea. Okay, so what is the actual solution? It's very easy. For a div1f anyway. You brute force the first 1,000. For everything after that, you just look 34 back, and then you just like calculate the pile sizes, right? So we count to see if anyone wins off the bat by having too many things. So Alice or Bob can win there, and then otherwise we look at the group sizes and we look at the group sizes and we run grunny numbers on them. Okay, I know that was like a very confusing explanation. Maybe I could have done it better, but that's what we got for today. Anyway, thank you for watching. I hope you enjoyed the contest, and hopefully you had as much fun as I did on getting this the last minute. Or anyway, hopefully your rating just went up if you enjoyed it. All right, that's all. Have a great day. Goodbye.